Okay, welcome everyone to the 52nd episode of the SFU Sports Analytics Virtual Seminar Series. It's my pleasure to have Dr. John Stockie here from SFU Mathematics. John has been a longtime member, sometimes attendee, and someone who I've had the pleasure of meeting several times and chatting with. So he's a full professor of mathematics at SFU with research interests that cover mathematical modeling, fluid dynamics, and scientific computing. The project that he'll speak to us about today stems from a lifelong interest in sport, which is cross-country skiing, as you can see from the title, that led him to develop an undergraduate course on the mathematics of Olympic sport in 2010, which he has since taught regularly. Combined with his personal passion for Nordic skiing as a recreational skier, coach, race official, and occasional racer, it was inevitable that he would eventually attempt applying math to solve this challenging problem. So cross-country or Nordic skiing involves a fascinating combination of physical processes, including forces due to propulsion, gravity, snow friction, and air resistance, as well as aspects of athlete strategy and sometimes rapid changes in course conditions, so from the weather and whatnot. This talk presents a dynamic model for a Nordic skier moving along a real race course extracted from GPS data. Numerical simulations of the resulting system of nonlinear ordinary differential equations are compared to data from actual skiers, and conclusions are drawn related to athlete strategy. So with that, I'm going to hand it over to you, John. I'm going to have you share your screen, and I'm going to mute myself and let you run the show.
Okay, thanks. Thanks for having me, and thanks to everyone for coming. I just had an internet blip, so I hope my home internet connection has been pretty stable in the past. So I hope this is not a problem. So I'm just gonna share. Just give me a second. Uh, Let me get this up. How is that?
It's good, John.
Okay.
All right.
So what I'm going to talk about today is a project that's been many years in the making, but has kind of gelled over the last year or so. And it has to do with modeling cross-country skiing, sort of aiming at a race with high-performance athletes. So this was a collaboration that I had with two postdocs. I just sort of posed this in a weekly meeting as something that might be fun to do. And Jane and Raphael were very keen, and it was a very fun project that we worked on last summer. I've also had some help from people involved with the Nordic skiing community. Caden Sim, who's a Nordic racer, but also a GIS specialist. Jake Weaver is an award-winning local coach with the Hollyburn Cross Country Ski Club. And Al Maddox and John Alberg helped with some of the course measurement rules that I had questions about. So, um, this is an outline of my talk. I'm going to give a little short background on cross-country skiing for those who may not know so much about it. And then the two main parts of the talk are the problem really divides naturally into two bits, which is approximating a ski course using a piecewise polynomial curve, and then using that curve in an OD model for the dynamics of a Nordic skier. So we'll show some numerical simulations that I would classify as preliminary. We have not shown these to sports scientists, so I'm happy to hear criticisms from people like you that may know more about sport. Um, but it's just trying to give you an idea of how some fairly simple ideas from applied math can help in terms of understanding a sport like Nordic skiing. So to sort of start with skiing, Nordic skiing has been around for a very long time. It originated in Scandinavia over 5,000 years ago, simply as a method for traveling over snow. And skiers propel themselves with a combination of forces transmitted through both skis and poles. And the technology of skis has changed a lot. They were originally simply wooden slats peeled off of trees, but today are fairly high-tech combination of materials. Um, the Throughout the history of Nordic skiing, as I said, it was mainly a mode of transport, but it was used for winter hunting as well, and then more recently for um, carrying out military exercises. And it was a way for people to patrol borders where there were no roads heading into the borders or where the roads were snow covered. In the 1700s was the start of Nordic skiing as a sport, where the Norwegian military held military competitions on skis, sometimes involving shooting. The first sort of organized international competition was in the Olympics in 1924 in Chamonix, held several Nordic skiing events, including the military patrol on skis, which is depicted in this photograph here. And the next year was the first international skiing competition organized under the Fédération Internationale de Ski, or FIS, which is the international uh, uh, organization that takes care of both downhill and Nordic skiing and all the other skiing related events. So how did I get interested in skiing? I have a lifelong interest and involvement in sport, starting as a competitive swimmer and then going through recreationally sports like cycling and karate, kayaking on the West Coast. But I got very involved in Nordic skiing early on. My son was a racer, pictured here at the Whistler Nordic Trails. Um, but I also took on roles as a volunteer coach and race timing official. Um, I am not a high level official, but I somehow eked my way into the World Junior Championships in Whistler, and that's an amazing type of event to actually watch. And I was lucky enough to be standing there at the start with a lot of the athletes. Uh, Despite the Olympic rings being there, my son did not compete in the Olympics. That's just, they still have these sort of legacy rings from the Olympics. So I did want to make that point. Um, Sort of leading up to the Olympics, I was trying to capitalize on the hype over the Olympics, but getting students interested in non-specialist courses in math, and I created this course on math of Olympic sport. It did not cover skiing, but I did include a simple differential equation model for a running race developed by this well-known mathematician, Joe Keller, that has many aspects that can be applied to the study of Nordic skiing. And the main difference with skiing is that runners tend to run on relatively flat courses. Even when there's hills, the hills are not especially steep. So Nordic skiers have many more changes in elevation and curvature that impact the athlete dynamics, and that's part of what I'll be including today. Um, the the research that I do is also I study a pretty wide range of problems in physics, biology, and other areas where I'm really a mathematical modeler that enjoys applying methods of applied math and scientific computing to study real problems. And so this is kind of an explanation for my interest in this problem. Um, our our approach to studying this skiing problem is really I don't want to say we're doing anything really new here. This is based on a previous model published by some sports scientists, Moxnes, Sandbach, and Hausken. And the problem really naturally divides into two sub problems. One is to approximate the skier path with a smooth curve, and then to simulate the athlete dynamics along that curve. And this picture gives you an example of what's called a ski course elevation profile plot, which shows the changes in elevation on the vertical axis and the distance along the course. This happens to be a 49-kilometer course. Darn, am I still hooked in here? Could someone let me know? I
Yeah,
have
you're
some.
still, can you hear
I
me?
am. Okay, great. Yep, yep. Just making sure I had something funny going on with my iPad.
No problem.
So this elevation profile plot, you'll see a lot of examples of this throughout my talk. And I do want to mention we've submitted a paper based on this work. It's in the SIAM Review education column, so it's really geared towards mathematics education. And if you want to know more, I'll give you a link at the end of my talk. And I really want to stress we employ elementary methods taught in undergraduate courses. So, but it covers a fairly wide range of material that's covered in the undergrad applied math curriculum. The simulations are performed using MATLAB, and I've made the code open source. And the point here is that some fairly simple ideas uh, can be used to perhaps provide some useful and even surprising insights into a sport, this sport of Nordic skiing. So I'm going to start with the first step of the problem, which is approximating a ski course with a smooth curve. How do we actually do this? And we need data on real courses is really what's required. And so the type of data we have comes in two forms. One is this 2D elevation profile plot, which you've already seen an example of. And the other is GPS data that are typically latitude, longitude, and elevation on the Earth's surface. Those are easy to convert into XYZ coordinates on a surface patch on the Earth. And this is an example of a course from Toblach or Dobbiaco in Italy, which is the site of many FIS World Cup races, that's plotted in 3 dimensions. And just to demonstrate the differences, this is the equivalent elevation profile plot on the left. And it's essentially an unwound version of that course where the 3 dimensional course has been unwound into 2 dimensions, where the horizontal coordinate is measured. It's essentially the distance along this pink curve, which is projected into the XY plane. So those two courses are equivalent, but of course, the 2D course doesn't take into account any of the changes in direction or curvature along the course. Okay, so I'll be talking about both of those throughout my talk. Um, and I'm actually going to look at 4 different courses. Two are based on elevation plots that I've actually extracted from journal articles. One from Moxney's Sandbeck and Hausken, who I've already mentioned. I'm going to refer to them as MSH. There's a longer course, 15 kilometers, from a plot by investigated by Welde and co-authors, which I'll just refer to as Welde, and then 2 GPS data files that we have, one for this course in Toblach and another at Whistler Olympic Park, which I'll refer to as WAP. So these two courses I'll refer to as Ole and WAP. They're about the same length, and they both been the site of several FIS rated races. So this is just a picture of the Whistler course. It's a local course that shows the elevation plot at the lower left and a plan view from overhead, which is what you often see on maps of race courses. And our 3 dimensional GPS data is, of course, a combination of both of those changes in elevation and changes in direction. So I have to say something about FIS. And what happens with any race course that's sort of at the international or national level is it goes through a process called homologation, which is the measurement and certification process that FIS officials, actually FIS certified officials, have to go through such a course, measure it, and make sure that it satisfies certain criteria. And there's a 60 page book of rules that I've tried to compress into a list of 4 main points here. Maybe I'll start with H3, which is about the actual course itself, that there should be an equal balance, roughly equal balance between uphills, downhills, and undulating flats to give the athletes a challenge, but also allow them to really pick up speed on these undulating flats. The average slope is actually relatively small, 3.5 to 8 degrees. It feels a lot steeper when you're skiing on these hills, but the numbers seem small, but that's the average slope. Hills can go up to 10 degrees, uphill or downhill, plus or minus 10 degree slope. It can exceed that, but only on short sections of at most 10 meters in length. So these are the slopes that are much more painful to ski up. And this is giving the athlete a little more challenge in the middle of a race. The start and finish line, you'll see in this Whistler course that the start and finish are in the same area that's a relatively flat section. And those start and finish areas are supposed to be of length 100 to 150 meters. Okay, well, so that they're relatively safe and predictable terrain, but also where spectators can view start and finish. There are also limits on curvature in downhill turns. These are the most dangerous parts of the course, where there's a tight turn on a downhill where the athlete's moving at very high speed. And they've actually got limits on the equivalent of centripetal acceleration. So I'm gonna talk about that later in my talk. It's a bit hard to quantify, but I'll talk about that later. And then going back to rules number H1 and H2, these are more on the sort of data that's reported. One is that the data points have to be sampled at every 20 meters at least, and that the posted course length, so a 5 kilometer race, can in reality be up to 5% shorter or 10% longer from the posted distance. It's never exact, right? It's very hard to get an exact length because of the simply the layout of these ski resorts where these things are run. And it turns out, this will be a point I come to later, is that the GPS files we obtained, many of them don't actually satisfy all of these rules. And so if international race courses were run there, our data file is not the one that was used to certify the course, but it's the only thing we have. So I'm going to talk a little bit about that later as well. So how do we generate a smooth version of a course that's based on discrete data that we have from either of these two forms, these 2D elevation plots or GPS data files? So what we do is I'm going to start describing what we do in 2 dimensions. What we need is essentially a smooth curve, z as a function of distance. And I'm calling the distance xi, which is this horizontal distance that is measured in the xy plane of the 3-dimensional plot. But in 2 dimensions, I'm labeling this horizontal distance xi. And what we have is what uh, from this elevation plot, what we do is we sample points. And this is easy to do using a tool like WebPlot Digitizer that takes maybe an image, from a paper, and you can sample points, with a mouse along there. So we've got n plus 1 points. And then what we do is we fit a piecewise polynomial or spline to this data. This is a standard process from, numerical analysis. We fit a spline. So this gives me a curve capital Z of xi. Whoops. And it's convenient to have additional splines that represent the arc length, the actual length the athlete is racing, and the elevation angle. The elevation angle is very important in our skiing model. And these can be written in terms of this smooth curve xi and its derivative, dz dxi. So the arc length is this standard arc length integral, and the elevation angle can be written in terms of the arc tangent of the slope, dz dxi. And these are also fit with splines, but this is easy to do in MATLAB. Once you've set up a spline for z as a function of xi, you can use these functions, function integral and function derivative, fn int and fn dir, to compute the corresponding splines for the arc length and the elevation angle, which essentially do integrals and derivatives of the spline coefficients. So this is all done, behind the scenes, but it's a very convenient way to compute these arc length and elevation angle splines very easily directly from the spline for Z. Okay, so if we actually look at the different choices of spline interpolation available in MATLAB, there are linear splines, there's splines of any polynomial order. We're going to focus on cubic splines, but using the linear spline as a comparison, since this is one that's actually been used by several sports scientists for simulating races. So the linear spline is available with this MATLAB function, interp1. It's not smooth. It's this, if you zoom in on this elevation plot, it's this piecewise linear curve that has these cusps at the data points, which is obviously not desirable when simulating an athlete moving along a ski course. There's the standard cubic spline, which is shown here with the dashed black line, and you can, or sorry, dash blue line, and that you can see has overshoots and undershoots relative to the data, which are especially obvious in this plot near the finish, which is very flat. You get these really non-physical looking oscillations, which are undesirable. So then there are spline interpolants that are intended to minimize oscillations. One particular spline that does a good job of that is the cubic Hermite spline. So it reduces the oscillations, but there's actually a modified Hermite spline that's called the modified Akima spline, or Makima. And this turns out to be the best choice. This is the one that's actually used in our model and that's shown in red with this red curve. And you can see that at least visually, it seems to be a much truer representation of a ski course that does not have any funny oscillations in flat areas in this bottom right plot. So that's the spline that I'll be using from now on. Now, if we want to use similar ideas in 3D, a three-dimensional course is really a space curve, which has three coordinates that we're also going to parameterize in terms of this distance in the xy plane, this xi variable. So the first thing we need to do is to take our 3D GPS data and obtain coordinates x, y, and z for each of these points. Now, it turns out I don't know, these don't give me this projected distance in the xy plane, this xi. And so I actually need to compute that. But this is easy to do in terms of an arc length integral, but arc length in the xy plane. So what we need to do is have a parameter that we can do the arc length in, and we're essentially choosing the parameter that's the point index, and then basing an integral on that parameter. So the same way that we computed the arc length integral in the previous slide, we just do this projected arc length curve to get coordinate values for xi. Then we now have values of xi, x, y, and z. So we can then generate spline interpolants for x, y, and z as functions of xi. We can also compute the arc length. We can compute the elevation angle. And it turns out for the skiing model, it's convenient to also have values of the azimuth angle, which is the direction angle depicted here. Sort of it's the direction angle projected in the xy plane. And we'll also need values of curvature. I haven't written the curvature formula here, but it's essentially the inverse of the radius of curvature at any point along the course. And these are all available, again, using these spline integral and differentiation functions that are available in MATLAB. Okay? So this plot of the Ole course that I showed earlier in an earlier slide is actually a modified Akima spline. So this work has been done. And now I'm getting into the heart of the talk, which is actually how we use these splines to model skier dynamics. And there's sort of two sets of differential equations that we get. One is for the actual dynamics, which is the forces and how they feed into Newton's second law for the motion of the skier. And then there's the kinematic equations, the ODEs for the geometric variables that have no physics. They just describe the sort of geometry of the skier throughout the race. And again, I'm going to start doing this in 2 dimensions. So a skier propelling themselves along a course with an inclination angle experience, depicted in this sort of diagram here on the right. I want to look at the forces in the direction of motion. So the skier is going up this hill with elevation angle theta and experiences a combination of four main forces. One is due to the forward propulsion from their muscles. Let me spend a little time explaining where this formula comes from. This is a propulsion force that's a muscle power being generated, but it has a 1 over v dependence because as the skier is moving uphill, they're moving at slower speed and have to generate a much higher force, although the actual power they're generating from the muscles may be the same as on other areas of the course. And this is a functional form that's been fit to experiments by Moxnes, Sandbach, and Hausken. So I'm just going to use this function. This is their power function that they used as a function of the skier speed. It has several parameters, P max, B, and this exponent n that I'll be simply using the values that they had in their paper. Because we have no way of actually measuring these ourselves. So this power function describes the main force propelling the skier forwards, but then the skier is also experiencing forces due to gravity. The component of the gravitational force, which is vertical in the horizontal direction, is minus mg sine theta. Now, what I forgot to mention is that for reasons of convenience, I've written all these forces in forces per unit mass. So you'll see here this propulsion force is actually divided by mass. The gravity force is missing the m in mg. I'll show you later where the mass comes in Newton's second law, but I've written these per unit mass. So similarly, there's a force due to friction with the snow that's minus mu mg cos theta. Force per unit mass is divided by m. And then there's an aerodynamic drag, which is given by the sort of standard proportional to the square of the speed. So it's a force that goes up with speed, but quadratically with the athlete speed. And I just want to make a note that the MSH power function here is one that incorporates the effects of the slope indirectly through the speed. So when they're on an uphill, they naturally are moving at lower speed, which gives them a larger propulsion force. They need to exert more force to make it up the hill. Whereas on downhills, they are at higher speed. Higher V means smaller force. And this is not because the athlete can't propel themselves with higher force. It's just downhills is where they tend to rest and recuperate their energy on downhills. So that's the purpose of this propulsion force from MSH. So now we can look at Newton's second law, which simply says that mass times acceleration is the total force. Here's the total force, each of those forces per unit mass multiplied by the skier mass m, and then mass times acceleration, okay, where we've used the prime to represent the time derivative. And the reason we define these as forces per unit mass is now the mass divides out of at least 3 of these force terms, and the only place the skier mass appears is in the propulsion term, okay? And so this differential equation is at the root of our skier model. It has a 1 over v singularity, which means that we can't actually simulate the skier from the start of a race where their speed is 0. So instead, what we do is we give some small initial speed that's positive, maybe a second or two after the start of the race. So that's a minor disadvantage of this form of the power function. Okay. So There are a couple of additional ODs that come from the geometry. I'm going to just talk very briefly about these guys. I want to be able to keep track of the arc length along the skier's path. This is the actual distance they travel. And this is the simplest possible OD, which is just that the rate of change of arc length is the speed that the athlete moves at. And this parameter that we're using to parameterize the splines, in order that I can evaluate the location of the skier along the course and things like that, I need to be able to keep track of this projected arc length variable xi, which is simply given by v times cosine theta, its time derivative. And then we give each of these time-dependent quantities initial conditions that they're zero at the start of the race. Okay? So we end up with a system of three ODs. They're nonlinear ODs with additional nonlinearities. Well, there's, dependence on sine of theta and cosine theta, but theta is actually a function uh, of this projected arc length variable xi through these spline evaluations. So it's kind of a nasty nonlinear ODE, but it's very simply computed through doing these spline evaluations for the elevation angle and the elevation angle and the elevation z. Now, I want to make the point that this is very similar to the MSH model, except for whatever reason, they don't really explain why, but they actually approximate the projected arc length with the actual length that the skier travels along the course. In their model, they replace the sine of the angle in the gravity and snow friction terms with z prime, their spline, as a function of arc length, not xi. And this is okay to do when the elevation angle of the course is small, like less than or equal to 10 degrees, which is the case at most locations along the course, but it's still an approximation. And the other thing they do is they use a linear spline for Z. And this means, among other things, that the elevation angle, which is based on the derivative of Z, is only piecewise constant. So it turns out our approach is going to be definitely more accurate in terms of representing the course. And these quantities, xi, sine, and cosine of the elevation angle. Okay, so we're going to see how much of a difference that makes when we actually look at the results. So skiing in 3 dimensions, the ODs are essentially the same, except we do one thing that's new, which is introduce a braking force. And this braking force is a force that in actual races, skier use to slow themselves down on very steep and tightly curved sections of the track. And the way we incorporate this braking force is through a function that's zero, through a force that's zero most of the time on the course, but it's only turned on in downhill sections, so theta is less than zero, and where the centripetal acceleration is this quantity, curvature times velocity squared. And this is something that has to exceed some braking threshold. So some threshold, some minimum value of the centripetal acceleration. And these parameters I'll actually talk about on the next slide. But this model now with this extra braking force, we need to include some additional spline evaluations, but we also need this curvature variable. And the curvature from vector calculus is given by this nice compact formula, which if you write it in component form, actually involves derivatives of these spline component functions for x, y, and z. And these derivatives, again, are easy to evaluate in MATLAB in order to obtain the curvature. So nasty formula, but this is fairly easy to compute using a software package like MATLAB. Okay? So based on this, we're now ready to simulate skiers in both 2 dimensions and 3 dimensions. So what I'd like to do is to start with sort of a baseline test that's comparing to the results that are in Moxney's paper. And here's a list of the parameters. The the one little extra thing that they put into their model that we've also done is they look at a speed dependent aerodynamic drag force because athletes have, well, there are many techniques that athletes use through a race, but comparing the uphill and downhill racing techniques, there's a normal upright position where the athlete's body is sort of in an upright position. Let me show you that on this figure here, the sort of the athlete standing upright. The other position is at the upper left here, which is the tuck position, which is an aerodynamically more efficient position that athletes use on downhills that saves them a lot of time. And that's what this speed dependent drag force tends to do is on downhills when the speed is high, they tend to move into this tuck position, which is a lower drag position. And it's a very simple way of incorporating this, but we've, just to be consistent with Moxney's, we've done the same thing. So let me show you the results from that simulation using the same parameters. With our Makima spline, we obtain a race time of 823 seconds. In order to be consistent with Moxney's, we also used the linear spline, which is pictured here in a zoomed in view of one section of the course. We obtained a significantly lower time, 10 seconds faster time, 813 seconds. And that's natural because the linear spline is the minimum distance joining all of those points measured along the curve. And so this is plotted as a time versus speed curve here. And you can see that the piecewise linear curve, the dotted line, ends just slightly before, 10 seconds before here. And it turns out Moxney's simulation finished in 815 seconds. Now, their numerical method, we don't know exactly how they've implemented this. And so if we compare our linear spline result, 813, to theirs, 815, this is quite close. So we're pretty confident that's a fairly reasonable match. But I would argue that our smooth spline is a much more realistic measure of what's actually going on in the race. Because, as I've said here, only cartoon hills are linear splines. Okay. So we then move to Welde's experiments, which is on a much longer course. It actually consists of 3 laps. And it turns out laps 1 and 3, which are sort of separated here with these dashed lines, are actually identical. So to extract the data for that course, I just want to mention we used an automatic feature of this web plot digitizer tool. And you can actually see here how that, if you maybe focus on this region here, B, that's circled here in the first and third laps, there's a little blip here that's missed. In this A region, you can also see the third lap has some oscillations here that didn't appear in lap 1. So there's obviously some error in the extraction of the data from this Welde course. There's nothing that we could really do about this, but I just want to point those out. Those differences are magnified in the velocity plots here that are shown zoomed in for laps 1 and 2, where there's a lot more going on here compared to the first lap. And all I can say is this is all that we were able to do with the data that was available in Welde's paper. It's interesting that for a constant power function, the time that it takes the athlete to run the race on laps 1 and 3 should be nearly identical, and they're not. So this is this is actually the average speed on lap 1 and lap 3. You can see there's a significant difference there. And that can be entirely, well, pretty much entirely attributed to these differences in the actual geometry of the course. So I just want to mention there's some other things about this Welde course that it's interesting. Even they don't actually say that this is a FIS rated race course, but it's interesting to look at the FIS rules, the homologation rules, and see how we do. So the average gradient is supposed to lie between 3.5 and 8. It does. The minimum gradient there's some very steep downhills on our simulated Velde course, which seem a bit high. And the maximum slope on an alpine ski course is 45 degrees. And this is getting dangerously close or, dangerously high. So I think this is actually an error in our data that we extracted for that Velde course. This is kind of a dangerously steep downhill for a Nordic skier. The maximum gradient is, you can have a short, steep section that's 10 meters long. So this one might actually be okay. But you'll notice here that the start begins immediately on an uphill, which is certainly not a race course. So there's defects that are likely arising from our extracting the data, but also that Velde's data that they provided in their paper may not actually, if this is a race course, they might have omitted the start section, which should be relatively flat. Okay, so I do want to show some 3D simulations, and these are the real thing. I hope I have still a few minutes to talk about these. Um, we studied braking force in particular on tight downhill curves. This is a race that starts at the green point, so the athlete moves along the course moving uphill and then hitting a tight curve here in this circled region, another tight curve here, and another one here. There's other places too, but these are places where the athlete applies some type of braking technique. And we looked at two types of braking techniques, something that's called a step turn and a skid turn. And we were able to get some data from another paper that gave us a braking coefficient to plug into our model for those two types of turn. A step turn, which is more efficient, applies a smaller braking force, and a skid turn, which is kind of like a plow turn where the athlete, where the skis slide around the corner instead, and that generates a higher braking force. And we also applied two different braking thresholds for the centripetal acceleration. And what we found with our simulations was here I've given the total race time with no braking, which is about 820 seconds. And with the step turn and the skid turn, it only makes the race about a fraction, well, less than a second slower. It certainly slows the athlete down, but it's only about 0.35 or 0.77 seconds slower. If we use a higher braking threshold, the difference is even smaller. And sort of looking at actual skiers on races, this is a difference that's really too small to be reasonable. It's just you know these type of skid turns, for example, really slow an athlete during a race by at least a few seconds. So there's something that we're not capturing here correctly. So you know, we're looking at ways to make the braking more realistic. And one of the things that we could do is to actually allow the skier to decelerate in advance of a tight corner. They don't actually brake only at the very tightest location where the curvature is the highest, but they actually look ahead, see these tight corners, and then start slowing down a little bit in advance to avoid wiping out in the very steep corner. So it I think it's much more reasonable to incorporate some kind of look ahead where they're looking ahead in the course to see where the large curvature is, maybe 10 to 20 meters in advance is what my racer son tells me is sort of the sort of distance that an athlete would look ahead to slow themselves down. Um, I do want to say this is work in progress. We've attempted this look ahead currently. It's breaking our ODE solver, and we are looking at other ways to try to incorporate this into the model. I do want to say we've sort of looked at the homologation criteria for this OLE course. It turns out the most obvious reason why this is not data that were used to homologate a course is that some of the GPS points on the Ole course differ by up to 120 meters. So they obviously break the 20 points, 20 meters per point spacing threshold for a FIS course. So it's clear that this GPS file was not used to homologate the Ole course, although it clearly is used in World Cup events. Again, I do want to mention that the starting area had a plus 6.3-degree slope, which is the start must be flat. And so my guess is they probably omitted the starting area when they created that GPS file. Okay. So um, uh, I just want to do quickly one more example from the Whistler's 5 kilometer blue course that was used in the Olympics. Um, it does actually satisfy all the homologation criteria. The finish has a slight uphill, but it turns out that's something that's desirable. If you actually read the fine print in the homologation manual, the finish actually is not supposed to be flat. It's supposed to have a slight uphill so that athletes are forced to apply a more like a faster technique that is actually more exciting to watch. And this is actually written in the homologation manual. This plus 2.7 degrees is actually meant to make the race more exciting for spectators. Okay, so that's actually an interesting thing. And then we did some simulations using the maximum power parameter from Velde's paper for elite skiers. So we took Moxney Sundback Hausken's number 274 joules per second, which is the power value, and increased it to 392, which is more typical of elite racers. And we got a race time of 776.6 seconds. Now, uh, I have no way to tell whether this is correct or not, other than comparing to actual races held at the Whistler Blue Course. And I looked at data back to the 2010 Olympics, and there was a 5 kilometer race there written as part of the relay. So if I looked at the average split time for the gold medal winners, that was 830 seconds. The fastest 5 kilometer leg of that race was actually 745 seconds. And so you can see our value for the race time actually sits between those two. And if you go to a more recent race, the under 16 boys at the World Junior Championships, the winning time was 773 seconds. So that clearly uh, is, I would classify them as an elite racer. And you can see that's very close to our results. So our simulations are able to get pretty realistic values for these, at least in terms of this race time. So let me just make some quick closing remarks about what we've done. This is a sort of summary of our results. So we generalized a two-dimensional model in the literature to three-dimensional courses, which is actually a new result. We incorporated this effect of braking on skid and step turns, which I've never seen before. So this is something that I would really like to look more at, perhaps talking to some sports scientists to get this more realistic. We focused on making sure that the algorithms were accurate and efficient. We validated our simulations using 2D data and then tried applying this to some three-dimensional courses that I think got some results that in the case of Velde were actually consistent with what was in the literature. And with the WAP course, we actually got some numbers that we could compare to real races. Okay. There's still some work to be done on our approach to simulating braking. And in terms of future work, we're looking at building in aspects of athlete fatigue. Right now, we have a constant power, maximum power parameter, but clearly in longer races, athletes sort of their ability to generate power decreases in the race due to fatigue. So we'd like to look at effects like this. So I'll stop there. I'm sorry for, I think I've gone a little overtime. My apologies. If you're interested in learning more, you can actually go to this website where we posted our article that we've submitted to SciAm Review. It's a very long review process, so it's been sitting there since September. It's actually an educational paper that has 17 additional exercises as supplementary material with solutions that are there, which are kind of fun exercises. And we've also got our MATLAB codes that are ready to run out of the box. The data is there, our GPS data and the data that we've extracted from other courses. And there's also a couple of movies, and I was hoping to show some of those in my talk, but didn't. I could take some time to show you a fun movie at the end if you'd like. But I'll stop sharing and take any questions people might have.
Great. Thanks, John, and no apologies necessary. You're perfectly within the time limits, and it was a fascinating talk. So I appreciate all the details on everything. Okay, so I'm going to open it up for questions. If you have a question, just raise your virtual hand and please ask away. And while we're waiting for others to chime in, so if I follow along, so you're creating a power function from the velocity data, correct?
Yeah, so it was basic. Well, so what Moxney, Sandbach, and how I did not create the power function. This was done in this MSH paper. There's been a lot of different uh, sort of functions that people have tried to fit to this data. But since they actually did simulations that were similar to ours on a course, we used the same power function and then applied it throughout. So this was fit. They used measurements of VO2 max. They did some various fitting of times. They did various things to try to make sure that this was a reasonable fit to what it wasn't elite athletes, it was fit athletes, I would say, that they measured in the lab, but then they actually did some outdoor simulations to see, comparing to their numerical simulations, whether this gave times that were consistent.
Hmm.
And so I'm sure you could do something a lot more sophisticated with that power function.
Yeah,
I'm already excusing myself,
excuse me.
but
No, yeah, I mean, just
yeah,
yeah, just I'd have to go back and kind of wrap my head around it. Yeah, you talked about fatigue, and that's sort of what comes to mind as a exercise physiologist as well. But like if you're, I guess if you like have velocity data from GPS and the course data, then like you're trying to solve for power in a sense. Like
yeah,
so in that sense, like fatigue is going to manifest in the velocity data
yeah,
already, and then so it's like yeah, like Pmax may decrease due to fatigue, but uh Pmax, like that would be like your maximal sort of sprint power, I think,
yeah,
at the end of the race, but that's not kind of like the defining function of like the sustainable power that the athlete would
yeah.
apply throughout the race. So yeah, it would be interesting to kind of look at sort of the power function for that. I know like I'm familiar with some of other Moxney's other work, and he's got some sophisticated metabolic type models. So I'm sure they put a lot of thought into that. Um, but yeah,
Yeah, and sort of coupling this with a metabolic model would be possible, but for a mathematician, it would be dangerous to do because I'd want to be a lot more informed before I tried
yeah,
that.
yeah, no,
Yeah,
no, I understand. Yeah, more parameters and things. But then you could be like, what's the optimal, obviously, allocation of metabolic energy, over the course, given the all these like really interesting changes, right? Like I'm
yeah,
just struck by the degree to which you went to simulate, the things like the curves, the braking. I mean, it's just the exquisite amount of detail is really something. I think, normally like when I think about, I have GPS data, all sorts of GPS data for running and cycling and things. And yeah, I've never even because of come close to contemplating trying to, do a full field-based simulation of that. But I think it's really interesting. And Mike
yeah.
Patton is here he's with Garmin, and so sure it would be interesting for them, to like be able to an interesting use case for their data.
Yeah,
Um,
so let me also say one of the results we have is it really worth simulating the curvature and the braking? Because at least with the example I showed, it only with the simulation I showed, it
yeah,
only made a difference of a fraction of a second.
yeah,
So there is a paper that we estimated the braking coefficient on where they do claim braking has a significant effect on the athlete results. That doesn't come out in our model yet. So I
yeah,
think we really have to do some work getting a more realistic model of what's going on with the braking. And I'm hoping this look ahead idea may help, but I would have to really discuss this with a sports scientist, someone who actually knows a bit more about racing. And that's my plan. We just, this has been more, like a mathematical fun so far,
Yes.
and it's going to be a lot more work. We do actually hope to publish something here in the sports science literature that focuses a little bit more on fatigue and braking, but we
Yeah.
have to be more careful
Yeah.
about.
Well, and that's, like I think when they tell you that it has an effect, I mean, it might be the fact that if you decelerate, then you have to accelerate again, and that's really metabolically costly. And
Yeah,
that would be missed
yeah,
from a sort of straight up power function.
yep,
Um, so maybe that, there's something on that front that
yep.
could be done.
Well, I'd be happy to talk to you or anyone else in the room about that sometime. I need, as a mathematician, I can incorporate functions, solution-dependent functions all over the place to try to mimic what's going on, kinematically, dynamically, metabolically.
Mhm.
But I need some insight into what's the right thing to do.
Yeah, no,
So,
I think it's fascinating, and
yeah.
yeah, like
Yep.
the possibilities like that, those, yeah, different way, even like I learned a lot about splines today listening to you. So,
Yeah,
and
I'm
then my
sorry.
my
I'm
student as
sorry to
well.
inflict that on you, but
No, no, like, no, I mean, they're so useful that I don't
yeah,
know anything about them, like enough, nearly enough to, and so like just knowing what these different functions and things is really helpful.
yeah.
I see that Tom Logan has his hand up, so Tom, take it away.
There we go. Hello, John. Um,
Hey, Tom.
if I try to imagine being a statistician for a moment, which is a stretch sometimes, um, you seem to have the ability to extract a lot of information out of a course, a lot of features and characteristics
Yep.
out of a course. And I wonder if one might be able to take those features and characteristics as, say, explanatory variables and look at individual racers' performance across different courses with different sets of features, and either use it as a training system where you say, oh, you know what, my racer really struggles in courses that have these features. My racer really goes great in courses that have those features. What
Yeah.
can we do to improve the training? Or simply just from a prediction point of view, you know what, I think if I'm going to put four racers together today in a relay team, given the course we've got, these are the four that I should choose. And
Yeah.
is this a kind of a thing that you could do with what as a side effect of what you're doing?
So I've absolutely seen a lot of papers where people are doing statistical analyses like these. Uh, you know, Measuring data of what an athlete is doing in very fine scale throughout a course, you don't really see. You tend to see things like say split times or times at various locations along a course, where people try to make general predictions about athlete performance based on that. So I've seen that, but these are the papers that I actually tend to ignore because I'm much more focused on people that are doing modeling and simulations or estimates of parameters that feed directly into my model. So I've seen it, but I don't know very much about it.
Right.
And
Your model
you
can
know,
extract course features, though, can't it?
yeah, yeah.
Yeah, and
So
that's what
one
I'm
thing,
thinking is now,
yeah,
okay, now I have a course that has this much curvature in it. Not all
yeah,
courses have the same amount of curvature in it. It has this much of the course dedicated to climbs, this much of the course
yeah,
dedicated to other features,
yeah,
and using those as sort of
yeah,
as analytical features to study as inputs to study the performance
yeah.
of individual racers.
Yeah, so one thing that is kind of discouraging from the standpoint you're thinking of or that you're describing here is that the FIS rules actually constrain things quite a lot.
Mhm.
They're constraining average and maximum and minimum curvature.
Mhm.
They're constraining the slopes and the percentage of uphills and downhills. And in the end, you look at these elevation plots, they look different, but sort of on average, they're all pretty much the same. You know
Mm.
what I mean? And so maybe this makes sort of studying that data a little less interesting. I'm not sure. However, if you would include courses like Cypress, Cyprus will never run a FIS race because it basically breaks every single, homologation rule, right? I mean, it's too steep. It's got too many hills. The hills are too steep. They're too curvy. Like it's on a mountain, right? I mean, it's never going to run a race. So, if you could get the data for more outlier courses like that, then maybe it would be a lot more interesting.
Yeah, the limitation
Yeah.
constraining the courses to be in certain aspects as similar as possible, it
Yeah.
would reduce the potential variability of the
Yeah.
data. But I would also imagine that there can be features like steep climbs early
Yeah.
versus not steep climbs early.
Yeah.
Are different racers going to be tuckered out by having a very steep climb early on, or are certain racers going to spend too much early and not be able to, they don't budget their energy and
Yeah.
and can't handle steep climbs later, or
So,
or
yeah.
or
So I tell you a personal story. There's a there's a loppet that's run every year. Loppet is it Swedish or Norwegian term for a fun race? Uh, and it's well, I usually run the 15-kilometer Loppet at Whistler, and they used to have the course set up so the start after the flat went immediately into the worst uphill climb. And you had like 100, skiers going immediately into this climb, and there were so many collisions and people that would just stop and sit, people like me that are out of shape that couldn't make it up that first hill. So after a couple of years of doing that, they changed the start to have a little more up and down at the
put the
beginning.
fun into the fun race.
Yeah, I know. So and that's the Whistler Blue course. That Olympic Blue course does have this initial climb that is fine for elite skiers, but for less fit skiers like myself and others doing that lob, it was just an absolute killer.
Yeah. All right.
Yeah.
Thanks, John.
Yeah, sure.
Yeah, speaking of loppets, John, I mean, presumably are those fists regulated, like, and could those be like a template for your model instead of like a
No, they're
fist?
not.
No.
But I would certainly love to, well, you know, this is just as long as I can get a GPS file or an
Yeah.
elevation plot, I can run this in the model, right?
Well,
So
there must be like Strava and everything. I mean, these skiers must be
yeah,
posting all sorts of GPS files.
yeah,
I
yeah.
mean,
No, so
I
there,
have one for my one ski outing from Whistler. Not that it would be useful to
yeah,
you, but
yeah,
yeah, like I'm thinking of the Gatineau 55, and then there's the Lachute. Like there's that ski marathon between basically Ottawa and Montreal.
yeah.
I mean,
So one of the interesting things I didn't really mention is this in Toblach, this Italian course. It's uh, connected, I believe, with Cortina d'Ampezzo, where the Olympics are run. And so they run a lot of FIS races there. And there were about 10 or 12 GPS files for FIS rated courses. And it turned out the Ole course was one of the only ones that was even close to satisfying the FIS rules. So they claim to be FIS courses, but the GPS files they provide were clearly not used for this homologation process. So the files are probably just files some employee went out and just sort
yeah,
of collected data. But
yeah, and there'd be
um,
a lot of error with those, I'm sure.
yeah, and there's very high slopes that are very suspicious. Like,
Sure. So, but
they,
you collaborate with that GIS person. I mean, are they, how reliable can you get like elevation maps? So instead of using the GPS elevation, use the projected elevation from a topographical map or something like that.
Well, I'm not familiar with that, but the GPS file that Caden Sim provided to me was incredible. The
Yeah.
resolution was down to like the smallest spacing of the points was zero point 0.8 meters, and the largest was, I think, 12.
Yeah.
And so it was very dense data, and I think I think he may have given me the file that was used in the Whistler Olympics. I haven't verified this yet, but it satisfied all the criteria. There were some steep slopes, but they were all within the boundaries that
Yeah.
are in the homologation manual.
Yeah, at least in like team sports where you have a lot of like collision changes of direction and
Yep.
accelerations and decelerations. I mean, the sampling rates on those GPS units are upwards of 20 hertz.
Yeah.
And, whereas a regular GPS watch that, you or I might wear cross-country skiing is 1 hertz. And that,
Yeah. So I
that's
think,
that's going to introduce a lot of, like you take a curve and now it's
yeah,
going to interpolate, basically between, and now you've cut off, a lot of that
yeah.
curvature that you would see otherwise.
So to be honest, I think most of the time the course data is actually well, as long as it's not too coarse. Like I mentioned, some of those point spacings went up to 180 meters. I think that's a little too far. There's a lot that can happen in a
Yeah.
180-meter stretch, but the Makima spline does a pretty good job of smoothing things out. So if you miss a really steep dip or peak or something like that, or a really tight curve. But I suspect that most people are sampling their GPS points precisely at those dips or peaks or curves. And then the Makima spline is going to interpolate those pretty accurately, I
Mm.
think. That's my that's my guess.
Yeah. Okay.
Yeah.
Any other questions? Going once, going twice. Okay, I think we're all out of questions, so let's all thank John one more time. Great talk, really interesting stuff, and
Yeah. Thank
yeah,
you.
thanks again for presenting.